Hey, welcome back. This is 8.8, and we're going to look at improper integrals. And to motivate it, we'll look at something called Gabriel's horn. Kind of on the web here looking at pictures of it. So what it is it's kind of an infinitely long horn. Okay, goes from, I guess, 0 to infinity. So maybe some other pictures of it. So it just keeps on going on and on, so you really can't show the whole thing because it'll go to the right forever. Okay, so it's kind of our goal here, and we can use 7.1 methods to figure out kind of the volume of that object. Right? I guess maybe we would want the surface area. Let's see if we can find the volume of it, right? If it has some sort of volume. So if we think about this chapter 7 stuff, we'll take Gabriel's horn to be modeled with the function 1 over x. Okay, so at 0, it's infinity, but at 1, it will be 1. At 2, it goes down to 1/2, and on and on. Okay, so we'll have this figure forever, going to the right forever. We're going to rotate it around the line y equals 0, and we're going to start at 1, so we're going to send our Riemann man in this direction, and we'll use a disk method. Okay, so let's get our little rectangle here. So maybe we should be doing surface area. I don't know. So anyways, the radius, then the radius function r of x will be 1 all over x based off this function, which is y equals 1 over x. And then our formula will be pi r squared, right? So 1 over x squared dx. The weird thing now is that we're, instead of going from 1 to like 5 or something, we're going from 1 to infinity. Okay, so that's kind of the new part that we're going to deal with in this section, is how do we, for one, I mean, there's other issues we'll look at, like discontinuities, but here we want to know basically if we can find a volume, because it could be that the volume is just infinite. So there's always this question, if I continually am adding, if the Riemann man is throwing in more and more volumes of disk as he runs along, does that disk just does that volume just get so big that we can't put a number on it, right? Is it just continually growing? Or is it kind of enclosed in sort of a box, so to speak? So you can think of like adding up an infinite number of things may not necessarily add up to an infinite number, right? So if the way you're adding it up, for instance, is take this box that has side 1, is 1 by 1, you could first fill up half of it, and then fill up another half of it, and then fill up another half of it, and continue on and on and on. You'll never fill up the box, but you'll be adding an infinite number of things together, right? So the things you're adding together will never be greater than basically the area of the box, which is 1. But you could do it an infinite amount of time. So it's kind of a weird paradox, right? If you're interested, you can go look up Xenos Paradox and things like that, that people were fascinated with. The box example is not, well, it's kind of like Xenos Paradox, but Xenos Paradox, I think, is usually given in terms of arrows or something like that, or crossing a room. So if you're trying to get from one side of the room to the other side of the room, you first have to cross 1/2 the room, and then you have to cross another half of the room, and then another half of the room. And the weirdness is, technically, you'll never really get there, right? Because you're constantly going half the distance, and you'll never get to the end. But in math, we just assume that you'll eventually touch the wall, and that kind of connects the real world to the mathematical world, and by saying that eventually you'll get to the wall. But anyway, so anyways, here we are. Let's get back to on topic. I want to find the volume of Gabriel's horn. So I'm using 7.2 methods, and I'll have so the trick to dealing with this is to rewrite the integral as a limit. So you can evaluate an integral if it just has these bounds, like 1 to b, and then you'll do that, but then at the end you'll just take the limit as b goes to infinity. Okay, so you'll have 1 over x squared dx, and of course you'll probably want to use a power rule, so you get the pi times the limit of x to the negative 2 dx, and then that'll equal pi times the limit of x to the negative 1 over negative 1, so negative 1 over x, and then we're evaluating from 1 to b, and we're taking the limit as b goes to infinity. Okay, so evaluate the thing, right? So pi limit, and what I mean by evaluate, I mean plug in the b and plug in the 1 into the antiderivative, right? So you get negative 1 over b. Hopefully I'm not actually muted. I don't think I am. Sorry. Well, somebody's taking a test. It doesn't seem that I'm muted. Okay, so I think I'm muted. So anyways, you know, you're plugging in b, and then you subtract away, plug in 1, right? So minus negative 1 over 1. Okay, and evaluate that, and then at the end you take the limit of it. So you'll find out Gabriel's horn actually has a finite volume. So here, the limit as b goes to infinity of, you know, cleaning it up, negative 1 over b plus 1. And as b goes to infinity, this part of the expression just goes to 0. So it seems that your answer is just going to be pi, right? Pi times 1. In other words, just pi. The volume of Gabriel's horn is finite. It's pi. Let's see if that's what they're saying on the web there. It seemed like I saw a picture where they had the answer. I don't know. Here it is. Okay. So yeah, so they're getting pi for the volume of Gabriel's horn. It's probably more appropriate to look at the surface area, and the weird thing about the surface area then, if you see, I guess that's what the second equation is, the surface area is actually infinite. So it's kind of like an interesting thing to study, that the surface area versus the volume. How can you have a finite volume but infinite surface area? It's kind of weird, right? So there's things in math that are like that, and hopefully that kind of motivates you to learn more about math and the weirdness of math, especially with regards to the infinite. You know, the infinite has been around for a long time, since, I guess, mostly in probably like religion, like people thinking that they'll live forever and some afterlife or something like that. So philosophers probably beat it to death. And some of the philosophers were like mathematicians, like Leibniz obviously was a philosopher, and he was also known for the development of calculus. Yeah, so anyways, let's take a look at the actual problems in 8.8 now. So that was kind of an intro thingamajig. Hopefully you found that vaguely interesting. There's two types of these improper integrals. So the one type we just saw was what they call infinite interval. Okay. There's other types, though, which are called like infinite discontinuities. So if you have something like the integral from 1 to 3 of dx all over x minus 2 dx, on this interval of numbers going from 1 to 3, because you can always kind of think of an integral as finding area, right? So you're going on the x-axis from 1 to 3. This function x minus 2 has an asymptote right there. So, it looks like this. And to find kind of, that integral, we're integrating over that region, right? So that's a big issue. And what is this called? It's called an infinite discontinuity. And the way you handle these things is with limits. Okay, so what you do is kind of drop the bound that's giving you trouble, or in the infinite discontinuity case, we would kind of cut it in half and then drop the issue. So you could, and I'll sort of go through the techniques as we go through the example problems. But for this one, you could kind of cut it into two integrals, and then take limits as you approach the discontinuity at 2 on both integrals. Okay. And I just saw that I have 2 dx's. That's not something, that's not new. Okay, that's just me screwing up. Okay, so let's dive right in then and kind of see if we can get through these problems. I'm going to be periodically checking this student taking this exam. I'm making sure he's not screwing around on me. Maybe I should set up my screen a little better so I can see him. I apologize. Okay. Oh yeah. This is so annoying. Put him to the side here. Okay, so anyways, let's take a look at some example problems. And some of them are pretty easy, but some of them can get pretty ridiculous. Anyways, let's take a look here. Let's just dive right in. Okay, so example, this first one, 1 to infinity of 1 over x cubed dx. So the real issue with this guy is this upper limit on the integral going to infinity. So what you do is kind of just turn it into a definite integral by replacing that sort of trouble limit with a variable. And then you'll integrate this thing, right? And then at the end, when you're done integrating, you just take the limit as this b value goes to, in our case, infinity. Okay. Seriously. Hey, Stephen, I can't see your webcam. All right, thanks. Yeah. Right, so this is the limit as b goes to infinity of the integral of x to the negative 3 dx, right? So we want to integrate that character, so I get the limit as b goes to infinity. I gotta make sure I'm still videotaping here. Yeah, so you keep saying I'm on mute, but I'm on mute in WebEx, so I think I'm good. Okay, so anyways, add 1 to the old exponent, so you get x to the negative 2 over negative 2. So in other words, negative 1 all over x squared. And we need to kind of evaluate it from 1 to b. Okay. All right, so then we'll have a limit that we have to take. So you have the limit then as b goes to infinity of negative 1 over b squared minus negative 1 over 1 squared. And then that'll equal the limit as b goes to infinity of negative 1 over b squared plus 1. Okay, so that first part, as b goes to infinity, this part will definitely go to 0. Okay, because that denominator gets huge. It's L over infinity form. Those always go to 0. Okay. Okay, so you'll end up with just the limit of 1, which is equal to 1. Okay, when you get a finite number out of it, so like in the case of Gabriel's horn, we found the volume was pi. That's called being convergent, and that word's going to come up later in chapter 9, again, when we start worrying about other things, okay? But convergent is basically the name if it equals some numbers. So compare and contrast that probably to this next example, which I think is called divergent. Okay, so they got 1 to infinity of 3 all over the cube root of x dx. And it's the same kind of problem, right? So you see, all right, I can replace this with a b. Let's rewrite the integrand, so it's a little easier to evaluate. And then, of course, we need to take the limit as b goes to positive infinity when we're done. Right. Okay, so what do we have then? So I have the limit as b goes to infinity of 3x to now the negative 1/3 plus 3/3 is 2/3, and then times 3/2, evaluated from 1 to b. And then that's going to equal the limit as b goes to infinity. And now I want to plug the limits into the antiderivative. So I have 9/2 b to the 2/3 minus 9/2 times 1 to the 2/3, which is just 1. And what are you ending up with? Well, this thing right here, as b goes to infinity, that's going to go to infinity. Okay. So you can imagine putting in 100 to the 3/2, 200 to the 3/2, 300 to the 3/2. If you put that into there, you're going to get 100 times 9/2, 200 times 9/2, 300 times 9/2. It's just getting huge. And then you're always subtracting off a constant. And the constant isn't going to really do anything. It's just like you have a sequence going 10, 100, 1,000, 10,000. If you're subtracting off just a little bit each time, it's going to be like 999, 999. It's still going to go to infinity. It's just going to be like one step below the other. It'll affect the speed that it goes to infinity. Okay. So at the end of the day, you're going to end up with infinity as your answer if you take the limit of that thing. And when you get infinity anywhere, you call that divergent, and you just you're done with it. Okay, let's look at one in the other direction. This one's a little more annoying. We have the integral of negative infinity to 0 of x e to the negative 4x dx. Okay. So this time the troublemaker is on the lower limit of the integral. So we're going to, as usual, replace the troublemaker with a variable. We have x e to the negative 4x dx. And then we're going to take the limit as b approaches that troubling limit. So in this case, negative infinity. Okay. Then we're going to integrate. And of course, this is an integral by parts. I like to do the tabular method now, and I plan on doing a video for the tabular method. That was suggested by Robert Shaw, who is a student in our classes presently. So if you want to meet the man behind the legend, you can talk to him in chat during WebEx or whatever, if he's willing to talk to you. I don't know if he will be, but he's in our classes, and so I'm going to use the tabular method. So the tabular method, what do you have? A sign, and then you have kind of take derivative. That down arrow means derivative, up arrow means. So you do this instead of the UV method. Okay. So you're going to go plus, minus, plus, or however far you got to go. And then you have Lie says algebraic before trig, so you're differentiating the x and you're integrating e to the negative 4x. Okay, so the way this works is you go down one row. Okay, so let me get this kind of rewrite the limit and get that started. Okay, so you go down one row and you're differentiating here, so you get 1, and you're integrating here, so you get negative e to the negative 4x all over 4. And then what you do is write this part. Okay, that's the next kind of part of your answer. So I'll have negative x e to the negative 4x over 4. And then you ask yourself if you know how to integrate this row. If you do know how to integrate this row, then that'll be your what you do. If you don't, then you go down another row and write out the next diagonal, and then ask yourself if you can integrate that next row. Okay, so I'll do a video on that. I wasn't planning on to, but I'll do a video on it. But if you need to, you just do by parts, and you'll get the same answer as what I'm doing. So anyways, the next step then, we have a negative times, so minus the integral of, okay, so it'd be minus then the integral of negative e to negative 4x. So you could factor out a 4 and a negative, and that would be plus 1/4 e to the negative 4x dx. Of course, we have to evaluate all of this junk at the end there. So that's going to give you limit as b goes to negative infinity of negative xe to negative 4x over 4, and then this will be minus e to the negative 4x over 16. And we have to evaluate from b to 0. Okay, that's going to be a nightmare. So plugging in 0 first, you'll have 0 times e to the 0 all over 4, that's just 0, minus e to the 0 over 16, that's 1/16, minus, now I plug in b, so negative b e to the negative 4b all over 4, minus e to the negative 4b all over 16. Okay, right, so as we go to negative infinity, the weird thing about these negative exponents is that they'll become positive exponents, and it kind of seems like this. So what's going on? This part right here, when I plug in like negative exponents, because I'm going to negative infinity, you're thinking negative 10, negative 100, but when you plug it in there, it's going to be negative 4 times 100, negative. So it's going to be 40, 400, 4. So this thing is going to infinity. And then it's times this negative b thing. So if you're putting in negatives, that become positive. So it's like infinity times infinity. This thing is going to be going to infinity overall. And then if you look at this critter, it also is going to infinity. So you have one of these infinity minus infinity scenarios that you have to find. You know, how did we learn how to pull that off? We find a common denominator and that sort of thing. So let's deal with that. And then we could probably do L'Hopital's on it, right? You could always kind of split up the integral so long as you can evaluate each independent integral. But let's see what happens if we do this. Okay. So what do we have? We have negative 1/16 plus b e to the negative 4b. I'm going to need a 4 in the top and bottom here, so 4, and then minus just e to the negative 4b all over, what do we have then, 16, okay. And then that numerator thing there, we can factor it a little bit. So we'll have the limit as b goes to negative infinity of negative 1/16 plus, I can factor out what? An e to negative 4b times 4b minus 1 all over 16. 4b, and this should be, if I distribute a negative, that would be plus. So 4b plus 1 is a line with a positive slope. So if we go to negative infinity, that's going to give us a negative infinity in there. So this part here is going to be shooting off to negative infinity. And then this part here, again, is shooting off to positive infinity. So the end result is you have a positive infinity times negative infinity, which of course is negative infinity. So you have an L plus negative infinity, which is just going to be negative infinity. In other words, it's divergent. Okay, great. Let's look at one a little more complicated here. It has two infinite symbols on it. So in our example here, negative infinity to infinity. So we're just integrating over the complete number line of 16 plus x squared dx. And let's see what happens. So how do I set this up? Well, you're going to have to turn it into two integrals. So you just split it wherever you want, usually at 0. Plus the integral from 0 to infinity. There should be a dx somewhere. And then we can go ahead and take the limits of these things, Okay, and the way I'm going to do it is kind of set it up like you wouldn't do arithmetic and addition in arithmetic class. So I'm going to do the first integral, so the limit, and replace the negative infinity with a b. And I think this way is a little easier to kind of stomach, and then plus in the other integral down below it. The deal being that if either integral is infinity, you just kind of stop, and it's automatically divergent. Sometimes you'll end up having to do really long integrals, you know. So if you could find that just one of these parts, either this part or this part is infinity, you can kind of just stop, right? Because you'll know it's automatically divergent by the definitions given in the book. Okay. Okay. So anyways, I want to go ahead and figure this guy out. I need to set up my limit too. So this one is going to negative infinity. This one's going to positive infinity. Okay, this thing is clearly just an inverse tan with a value of 4. So I have the limit as b goes to negative infinity of 1/4 tan. And I got another 4 in there. So 4 times 1/4 is just going to be 1. I have a feeling I'm going to need some more room. So I got tan inverse of x over 4, and I'm going from b to 0. So substituting into the antiderivative, I'll have tan inverse of 0 minus tan inverse of b over 4 in particular, but just putting b in there won't make a difference. We'll get the same answer. So b over 4, and then we need to evaluate that. So to evaluate that, just as b goes to negative infinity, kind of think of the inverse tan function. Inverse tan function, it looks like this. Okay, and it has asymptotes at negative pi over 2 and pi over 2. Okay. So as we approach negative infinity in this direction, the graph is going to approach negative pi over 2. Okay, with that top asymptote is pi over 2. But as we go towards negative infinity, this thing will shoot off to negative pi over 2. Tan inverse of 0 is just 0. You can say it's 0, 0, that point right there. And then what you get is, of course, negative pi over 2, which is pi over 2. Okay, the other integral is pretty much the same spiel, except has different limits there, right? 0 and b. We have two independent. So limits, the bottom and top thing on the integral, those are called limits, but we're also taking the limit of this thing. The integral is technically kind of just a limit anyways. If you remember the definition, it's the result of taking the limit of the Riemann sum, right? So it's a little confusing because there are two limits kind of floating about that we're dealing with. So I apologize on behalf of the people who taught me to teach you this, but that's kind of what we're dealing with. So anyways, once all is said and done, you're going to have the limit of tan inverse of b all over 4 minus tan inverse of 0 again. As b goes to infinity, then in this other direction, tan inverse is going to positive pi over 2. So this thing will go to positive pi over 2, and our answer there would just be pi over 2. The other guy, tan inverse of 0, is just 0. So this is pi over 2. Okay, and then ultimately we need to add these together. So pi over 2 plus pi over 2 is pi. And that is our answer, and so therefore it is convergent. Okay. Okay. Let's move on. So now we're going to move into these infinite discontinuity problems, and let's take a look at handling these. Okay, so the first one we'll look at. So now it's kind of, maybe I should have headed these as this types. So first we're doing, this is like part A, infinite intervals. And then I'll do down here part B, infinite discontinuities, right? Okay, so the first one I'll look at is the integral from 0 to 1 of 1 all over x squared dx. Okay, so what you kind of do is look at this function and then see if there's any values on the interval from 0 to 1 where that blue circled function there is undefined. Okay, so clearly if you putting in 0 into this thing, it's trouble. You can't divide by 0. So there's kind of a discontinuity at 0. So what we're going to do, as usual, is just kind of replace the trouble limit on the integral, the 0 there, with a variable. And then you'll be evaluating that integral. And then at the end, you just take the limit. Okay, so it's pretty easy. Right, so the only issue, though, is kind of there's an approach to deal with. So you can imagine you're standing in this interval from 0 to 1, and for our limit, you're going to be then either going to the right or to the left, and it's dependent on where the discontinuity is. I'm going to be running towards 0. Okay, so I'm going to be taking the limit as b goes to 0 from the right. So you have to include that part, and a lot of students won't do that, but you need to include that. Okay, so let's see if we can pull this off then. Okay. So whenever you do these, you pretend you're standing inside the interval from 0 to 1, and then you're directing kind of your Riemann man to go to one side or to the other. Right? Okay. Let's go ahead and do this, right? So I need to evaluate this thing first and then take its limit. So I have x to the negative 2 plus 1 is negative 1 divided by negative 1. So I got negative 1 over x. Evaluate from b to 1. Plug in 1, plug in b. Okay, and what is this thing going to be? It's the limit as b goes to 0 from the right of negative 1 plus 1 over b. And if you remember, the 1 over b, if you plug it's an L over 0 case, right? So we're trying to figure out the limit as b goes to 0 from the right of 1 over b. Okay. So form L over 0 is always either positive or negative infinity, right? To figure out whether it's positive or negative infinity, you can do some test values. So you'll have your b value that you're plugging in that's getting close to 0 from the right. So here's 0. I'm coming in from this direction, so points like 0.1. And then you're plugging that into 1 over b. So if you plug it in, you'll have a positive over a positive, which is positive. So we're going to positive infinity there. So right here we'll have negative 1 plus positive infinity, which will end up equaling positive infinity, okay? Which means it's divergent. Okay, let's look at another one. This one is the video quiz question. Video quiz, video quiz, video quiz, video quiz. Okay. All right, so let's take a look. The integral from 0 to pi over 2 of tan of theta d theta. Okay, so what's the deal here? What does tan of theta look like? Well, if you remember, tan is sine over cosine, and cosine is 0 at negative pi over 2 and pi over 2, so tan will have asymptotes there. In other words, discontinuities. Okay. From 0 to pi over 2, the discontinuity is definitely at pi over 2. And then if you think in terms of kind of like standing in the interval, your Riemann man is going to the right. He's approaching from the negative. So when we do our rewrite here, going from 0 to the troublemaker, the pi over 2, where the discontinuity is, we need to approach that troublemaker from the negative numbers. Okay, so if I'm going to the right, it's from the negative direction. If I'm going to the left, like up here, I'm coming in from the positive side. Okay, here's the negative side. Okay, so anyways, we just have to then evaluate this integral. So I'll have the limit as b goes to negative pi over 2 from the negative direction of the integral of tan is negative ln cosine, or if you'd rather ln secant, I'd rather ln secant. And then we need to substitute in our limits and our antiderivative, so we end up with the limit as b goes to pi over 2 from the left of ln of the absolute value of secant of b minus ln of the absolute value of secant of 0. Okay. Secant of 0 is 1, and then the ln of 1 is just 0. So this part is gone. That's just 0. Then the other guy. So what does secant look like? If you remember, secant piggybacks off of the cosine function. Here's cosine. Okay. So the secant function looks like this. And then down here it goes like this, etc. Okay. So as we approach pi over 2 from the negative values, what's happening to secant? Well, secant is going to go to infinity. Okay. So we're plugging in numbers that are going to infinity into the natural log function. Okay. So what is the natural log function doing as these values inside of it go to infinity? Well, it's going very slowly, but it keeps on increasing, increasing, and increasing. So overall, then this whole thing will go to infinity. And what you end up with is just infinity as your answer. In other words, it's divergent. Okay. Okay. Let's look at. So that was your video quiz question. Let's look at another one, if I can find one that's worthy of my. Okay. So let's look at one of these ones where the discontinuity is inside the interval. Okay, so from here from 0 to 2 of dx all over the square root, no, the cube root of x minus 1. Okay. Okay, so in our interval here, we're going from 0 to 2. Let's see, here's 0, here's 2, but there's a discontinuity at 1. Okay, so we need to split this into two integrals, going from 0 to the discontinuity. So it's just like kind of like when we had the infinity on both sides of the integral, and we had to split it into two integrals. It's kind of the same spiel. And then 1 to 2 of dx all over the cube root of x minus 1. Okay. Okay, I'm going to set it up the same way as I did before, kind of like an arithmetic problem. So I have this first one, taking the limit as b goes to 1. And in that first interval, the Riemann mat is approaching from the negatives. So that will be a negative approach. Let me rewrite the integrand a little bit. So let's not use that symbol. I want x minus 1 to the negative 1/3 dx. And then the other integral, approaching 1 from the positive numbers. Okay, so that'll be plus. And I have x minus 1 again to the negative 1/3 dx. Okay, so 0 to 1, and then 1 to 2. And here we go. Hopefully we'll be able to add them up. Okay. So the limit as b goes to 1 from the left of the antiderivative. You could do a u sub if you want to, but you don't need to, because u is just x minus 1, and then du is just dx. So you're just going to end up with u to the 2/3 times 3/2, right? And then you back sub and you get x minus 1 to the 2/3 to the 3/2 times 3/2. And then we want to evaluate this guy from 0 to b. That should be a b, sorry. These are both b's. Okay, so plugging in the limits into the antiderivative, we have 3/2 times b minus 1 to the 2/3 minus 3/2 times -1 to the 2/3 is -1 squared, which is 1, and then the cube root of 1 is 1, so you just get 3/2 on that part of it. Okay, and then if you plug in 1, you just get this thing being 0. And then you're left with apparently -3/2 for the other guy. Okay, so on the next part of the guy, it's the same deal, but with different, b to 2 instead of 0 to b. So limit as b goes to 1 from the right of, so how will this work? It's going to be 3/2. It's the same thing, x minus 1 to the 2/3. Evaluate this critter from 0 to b, so that'll be limit. B goes to 1 from the right of 3/2. Whoops, it's upside down and I used the wrong bounds. B to 2. So that's going to be 2 in there first. So that would be just times 1. 2 minus 1 is 1. 1 to the 2/3 is 1. And then minus, plug in the b value. So that would be 3/2 times b minus 1 to the 2/3. Again, when you plug in 1 for b, this part will just go to 0, and you'll be left with 3/2. Then if you add them together, you end up with 0. Okay, and that's your answer, and it is convergent. Okay. Alrighty then. Let's see if we have anything else. Yeah. Okay. The last problem we want to look at, an example here, is this, and it's kind of related to what we'll be doing later. Kind of related. Basically, an integral, you can kind of think of it as a summation. So you can relate it to things that look like this. N equals 1 to infinity of 1 all over n to the p. Okay, and eventually we'll be interested in these things because they're related to evaluating like the sign of 1, right? So you're all memorized the sign of pi over 3 is √3/2. How would I figure out the sign of 1? What's the process there? And it turns out we can represent functions that are kind of nicely behaved, or maybe elementary, or they even have fancy names for it, like I forget what they call it, analytic, right? If you take complex variables, they talk about analytic functions, and they could be written out in terms of these sums in a kind of a weird sort of way. So anyways, that's in the future, but we're going to be studying these things. They become important to us for whatever reason, and they are connected to these type of integrals. And in particular, we'll want to know if these things are useful, and if they're useful, we call them convergent, or just trash, and if they're trash, we call them divergent. And of course, being trash doesn't mean anything. If you know who Ramanujan is, he studied kind of the divergent types and figured out a way to classify them. So anyways, let's take a look at this thing, right? So ideally, I can just tell whether it converges or diverges just by the p-value here. So if you look back up here, I kind of knew the answer to question like let's see, like this guy right here, 3 over x, because you could rewrite it as 3 over x to the 1/3. And then this exponent here kind of tells you if it converges or diverges. If that value is in between 0 and 1, it's divergent, and we saw that was divergent. If it's greater than 1, like it was here, it's convergent. So we ended up with convergent, right? So it turns out you can play that game with these kind of things, and that's kind of what we want to investigate right here. So there's 3 cases for the p-value. The first case is when p equals 1. So actually 2 cases when you're integrating, right? So you either have a natural log integral when p is 1, or you're doing a power rule. So let's do this version first. So I'm going to, again, replace the upper limit of the integral with a variable, and then take the limit of it eventually as the variable goes to infinity. So 1 over x dx, that's just a natural log integral. Okay, or just call it a natural log. So it's the limit as b goes to infinity of ln of the absolute value of x, evaluated from 1 to b. So that'll be the limit as b goes to infinity of ln of b minus ln of 1, which is 0, so it's just ln of b. And as b goes to infinity, what happens to the natural log function? The ln of the absolute value of b looks like this, but we're going to positive infinity. So as we go to positive infinity, the y values are going to go to positive infinity. So this thing is divergent. So if p is equal to 1, the integral from 1 to infinity will be divergent. And we're also going to be able to then say the summation of 1 all over n to the first power from n equals 1 to infinity is divergent. And this is called the harmonic series right here. Okay, but that's for chapter 9. Okay, so let's look at what happens when p is not equal to 1. And then we could just use the power rule, right? So you have 1 all over x to the p dx from 1 to infinity. And we'll assume that I believe we want to assume that p is greater than 0. Okay. Okay. So anyways, we turn it into a limit as the upper limit goes to infinity. And we'll have x to the negative p dx. Then we can do a power rule on it. As b goes to infinity of, x, I'm going to write negative p plus 1, but I'm going to write 1 minus p divided by that exponent 1 minus p. Okay. And then I'm taking the limit of this thing, and there's two cases. So I have b to the 1 minus p all over 1 minus p minus 1 to the 1 minus p, which is just 1 over 1 minus p. This second part that I'm circling in red is finite. Okay, so it's not really going to affect the limit. The thing that affects the limit then is this thing in blue. Okay, and there's two cases there. All right, so the first case we'll look at is when 1 minus p is less than 0. In other words, when p is greater than 1. Okay, and then the other case is when 1 minus p is greater than 0, in which case p is less than 1, or of course p is greater than 0. Okay, okay. So when p is greater than 1, you'll have a limit as b goes to infinity of this blue thing, b to the 1 minus p all over 1 minus p. Because 1 minus p is less than 0, this thing will actually kind of go down to the denominator, right? And when you take the limit, it's going to be L over infinity form, okay? So it's kind of like if you were taking the limit as b goes to infinity of 3 to, or e to the negative x, this is one we've been kind of looking at lately, right? All over, or e to the negative b, all over, I don't know, 5, right? In that case, the e to the negative b drops down to the denominator, 5e to the positive b, and then this thing goes to infinity, so your n limit ends up going to 0. That's the scenario we're dealing with right now. So this will end up being 0. In other words, in this case, it's convergent. Okay, so if p is greater than 1, it converges, and that's exactly what we saw in the case when you had 1 over x to the, I believe it was third power, right? Yeah, it's squared. 1 over x. No, that's not it. Where'd it go? Here it is. 1 over x cubed. Yeah, that one's convergent. Converge to 1. So you probably use that formula there to figure it out. P was 3. You said P was 3. 1 minus 3. Seems like that's wrong. What is it? 1, 2, was it not 1 to infinity? Did I make a mistake there? Oh, I must have made a mistake. Yeah, I did. It's a good thing I kind of looked. Whoop. So this will be negative 1 over 2v. This will be negative 1/2. It ends up being 1/2. Right? How did I know it was wrong? It's because the formula is right there in red. Right? So if you plugged 3 in there for the formula, you get negative 1 over 1 minus 3, which is negative 1 over negative 2, which is 1/2. So the integral of 1 all over x cubed from 1 to infinity should be just 1/2. Okay. Okay. Then there was the other case up there with 1 over the cube root of, or like the, I don't know, the cube root of x or something. What was that guy? This guy. 3 over the cube root of x. So that should be infinite, because the p-value here is 1/3, which is less than 1 but greater than 0. So let's just make that clear. So in this other case, so I just did this case. This other case then, this one term, this b to the 1 minus p all over 1 minus p, the bottom is just a constant. Right, it's just, you know, something like p is 5. You know, you can imagine, or sorry, the p-value is less than 1. So you can imagine b to the, let p equal 1/2, right? So you get b to the 1 minus 1/2, which is 1/2, all over 1/2. And b to the 1/2 is just a square root function. It's going to look like this. So as b goes to infinity, b to the 1/2 also goes to infinity. And then if you in general, that will hold. Okay, so this other version will equal infinity, and so this case will be divergent. Okay, so it's divergent here and convergent there. So the whole, you know, in a nutshell, you can kind of put this all together and say that the integral of 1 all over x to the p dx is equal to, and there's 3 cases. It will be equal to negative 1 all over 1 minus p if p is greater than 0 but less than 1. Oh, sorry, no, if p is greater than 1, right? P is greater than 1. It'll be divergent. So this is a convergent case because it equals something. Right? It'll be divergent if p is greater than or equal to 1. Oh, sorry. I can't get the stupid eraser. I'm doing like 3 things at once here. P is greater than 0 but less than or equal to 1. There we go. Okay. And we'll see that same criteria pop up when we're doing the summations in Chapter 9. Okay, so I think that'll do it for this section. Sorry, I was kind of proctoring a test. It is just the way my life is going right now. I'm proctoring a lot of tests, so I apologize if that bothered you. Hopefully it didn't. I can't see why it would, but you can kind of like arrange your screen so you don't have to see it, but I don't know. So anyways, I'll stop talking and I'll let you go, and we'll see you next time.